Welcome to the University of Arizona and Steward Observatory's Richard F. Caris Mirror Lab. My name is Dr. Alan Strauss, and I'm the director of Steward Observatory's Mount Lemmon Science Center. Today is a very exciting day for all of us at the lab, as the sixth primary mirror segment for the Giant Magellan Telescope will reach high fire. We would first like to pay honor and tribute to the original inhabitants of this land. This region includes the ancestral homelands of the Tohono O'odham Nation and the Pasquayaqui tribe. The University of Arizona sits on the original homelands of indigenous peoples who have stewarded this land since time immemorial. Aligning with the university's core value of a diverse and inclusive community, it is an institutional responsibility to recognize and acknowledge the people, culture, and history that make up our Wildcat community. At the institutional level, it is important to be proactive in broadening awareness throughout campus to ensure that our students feel represented and valued. We have a very busy hour planned today as we share with you how these mirror segments, the largest telescope mirrors in the world, are fabricated, as well as the science that will be enabled when the Giant Magellan Telescope is complete. Throughout the afternoon, we will be checking on our furnace cameras, both outside and inside the furnace, as we prepare for the approximately 1:50 p.m. high fire, when the furnace reaches its peak temperature and the raw glass is filling the mold. Before we begin, I would like to acknowledge my colleagues behind the scenes today: Vanessa Gressieu, Debbie Federico, Kathy Duncan, and Travis Dio. They have all worked very hard to make today's event possible. Together, we are the staff that facilitate outreach programming, both here at the Richard F. Caris Mirror Lab, as well as at our mountaintop observatory, the Mount Lemmon Sky Center. Through all our outreach programs, we have a very, very simple goal. That is to take the excitement, the wonder, and the amazement that our guests arrive with, and through science, provide an understanding of the world and universe around us, an understanding that serves to deepen that sense of wonder. To get us started, I would like to introduce the president of the University of Arizona, Dr. Robert Robbins, who will be followed by Dr. Buell Januzzi, Director of Steward Observatory, Department Head of Astronomy, and member of the GMT Board of Directors.
Good afternoon. I'm Bobby Robbins, President of the University of Arizona. Thank you for joining us for this exciting milestone, the casting of the sixth primary mirror segment for the GMT, the Giant Magellan Telescope. These giant mirrors are marvels of innovation and engineering, and I'm so proud of everyone at the Richard F. Caris Mirror Lab for their contributions to making the next generation giant telescope. GMT will help astronomers, including our students, to make progress in answering the most important questions in astrophysics, including searching for signs of life on planets around distant stars. I hope you enjoy the program that Buell Januzzi and his colleagues have put together for you. Let's get started.
Thank you, President Robbins. Good afternoon and welcome virtually to the Richard F. Caris Mirror Lab. Today, we are celebrating the start of the casting of the sixth of a total of 7 giant mirrors that are required to complete the Giant Magellan Telescope, which will transform how we learn about the universe. The Giant Magellan Telescope is an incredible, bold, audacious project to build a facility capable of such diverse science programs, as you heard from President Robbins, searching for life on planets around other stars and studying the first stars that were formed in the history of the universe. Fortunately, we have a wonderful international consortium of founders for the GMT. GMT's founders are universities and science institutions in the United States and abroad. Our founders reflect a broad partnership that brings together scientific, technical, and organizational strengths that we need in order to build the GMT. The current founding institutions are the University of Arizona, the University of Texas at Austin, Carnegie Institution for Science, the University of Chicago, the Smithsonian Institution. The country of Korea is represented by the Korea Astronomy and Space Science Institute, Harvard University, Texas A&M University, Arizona State University. The country of Australia is represented by Australia Astronomy Limited and Australia National University. and the state of São Paulo in Brazil through the São Paulo Research Foundation. Each of our founding institutions have also been generously supported by many people, including philanthropists, and for the University of Arizona, this has been essential to our participation, and we thank you very much for your support. We are also pleased to acknowledge that the National Science Foundation has recently awarded a significant funding award to the GMT to help complete the development of the technologies that will be used by the GMT so that we can, in the future, be considered for additional funding to be part of the US Extremely Large Telescope program. Now, the GMT's ability to transform our science is a direct result of having a giant 24.5 meter in diameter primary mirror. The primary mirror of any telescope, like the one you see on the left of this slide, is the first optical surface or element of the telescope that sees or collects the light from the targets in space toward which we point the telescope. Having a diameter 10 times the size of the Hubble Space Telescope, the primary mirror for the GMT will enable the highest spatial resolution and most sensitive observations of the universe that we've ever been able to make. Now, here at the University of Arizona, we are the world leaders at making the largest optics for telescopes, but even our largest mirrors are only 8.4 meters in size. That's 27.5 feet. To make the 24.5 meter diameter mirror we need for GMT, we are actually making 7 mirrors that together, when mounted in the telescope, provide the giant combined mirror needed for our science. We call each of the 7 mirrors one of the segments of the GMT's primary mirror. How we make these large mirrors, get them into a modern state-of-the-art telescope, and use them to produce transformative science will be presented by my colleagues, and I'm going to introduce them to you now. Dr. Buddy Martin, who is the lead scientist for polishing at the Richard F. Caris Mirror Lab. Dr. Jim Fanson, the project manager for the GMT. Dr. Dennis Zaritsky, Deputy Director of Stewart Observatory. Dennis also serves as the chair of the Giant Magellan Telescope Science Advisory Committee. Following their presentations, we will have a question and answer session during which we will be joined by Dr. Roger Angel, who nearly 40 years ago started the Mirror Lab on the path of innovation and invention that have made it possible to make these giant mirrors, and still serves today as the director of the Mirror Lab. Buddy will now start us off by briefly describing how we make the world's largest mirrors for GMT. Buddy?
Thanks, Buell, and good afternoon. What we're doing today is the most dramatic step in a 4-year process to make a mirror. Not just a mirror, but one that has all the right qualities to let us see the faintest and most distant objects that can be seen, and to make the sharpest possible images of them. This step, that we call casting the mirror, means melting the glass into a mold that'll make a lightweight honeycomb structure. A mirror has to hold its shape to a few millionths of an inch, 50 to 100 nanometers, and it has in the telescope, and it has to do that while it's being hit by winds up to 20 miles per hour, while gravity's trying to bend it as the telescope points in different directions. Well, this mirror is very stiff because it's more than 2 feet thick. It's also 80% hollow, so much lighter than a solid mirror. It's stiff enough to resist the wind, and the stiffness, along with the reduced weight, makes it resist gravity as well. I don't mean it'll float away. I mean gravity doesn't bend it. The mirror also has to exchange heat with the air quickly so that the mirror will stay at a uniform temperature equal to the air temperature. If that doesn't happen, then the mirror creates turbulence in the air that blurs the images, like the shimmer you get above a hot road in the summertime. Well, this honeycomb mirror does stay very close to the air temperature, even as the air cools through the night, because the layers of glass at the top and bottom of the mirror are only an inch thick. We make the honeycomb structure by building a mold that's a large tub filled with 1,700 hexagonal boxes. When the glass melts around these boxes, it'll form the cavities in the honeycomb. The glass is a very pure type of borosilicate. It comes from the Japanese company, Ohara, and it's perfect for us because Ohara makes it in 1-ton clay pots and then carefully breaks each ton of glass into a few hundred small pieces like you see here. These pieces have such pristine fracture surfaces that they melt together with no trace of the individual pieces. So we weigh each piece of glass to be sure we put the right amount into the mold and then place it by hand on top of the mold. There are half-inch spaces between the hexagonal boxes. As the glass is melting right now, it's starting to flow down through those spaces, but it has a consistency like cold honey. So it takes several hours for it to flow down to form the ribs on the honeycomb and to flow partway under the boxes to make the back plate of the mirror. We usually think of glass as an optical material. Light goes through it. It's used for lenses. But for a telescope mirror, we use the glass as a structural material that can be polished to a precise shape. The aluminum reflective coating will be applied to the top of the mirror, so the light never goes through the glass. The sole purpose of this big piece of glass is to hold a thin layer of aluminum, only 1,000 atoms thick, and most importantly, to hold it in the right shape. Well, with the glass loaded into the mold, we installed the lid to close the furnace. We started heating it on Monday. It's gradually heated up to now the maximum temperature, 1165 degrees C, about 2100 degrees Fahrenheit. And we're just reaching that temperature approximately right now. When the glass reached 750 degrees yesterday afternoon, we started spinning the furnace at 5 RPM, and we want to show you what that looks like and give you a little feel for what it sounds like. Trust me, it's a lot louder than that in real life. We wouldn't be able to have this conversation right in front of the furnace. Well, as the glass melts, the centrifugal force from the spinning will push the glass out and up the sides of the mold, so it forms the curved parabolic surface that's approximately the right shape for this mirror. And that will save us months of grinding out that curve. As soon as the melted glass has filled the mold this evening, we'll cool it quickly, and within 2 days, it'll be down to 650 degrees C, at which point the glass is solid and we can stop the furnace rotation. But the glass is still soft at the atomic scale. The atoms will get locked into place at about 500 degrees C, and it's essential that the mirror is very uniform in temperature while that's happening. So we achieve that by cooling it very slowly, 2.5 degrees C per day for about a month. Another month and a half will bring it down to room temperature around June 1st. We'll take apart the furnace and the tub of the mold and get our first look at this mirror, first good look at the mirror. It'll still have the hexagonal boxes trapped inside, and we'll wash those out with high pressure water at the next stage of processing. And that will leave just the single piece of glass in this ideal lightweight honeycomb structure. Well, the mirror will then be ready for grinding and polishing, and that's a long, painstaking process, not nearly as exciting as the casting, but it's the process that creates an optical surface that's accurate to 1/1,000,000th of an inch, or 25 nanometers. None of us have a very good feel for what 1/1,000,000th of an inch is, myself included. So the way I like to picture it is to imagine the mirror expanded to the size of North America, 3,500 miles in diameter. Then the typical hill would be 2/3 of an inch high in the typical valley 2/3 of an inch deep. That's how smooth this mirror has to be for it to make images as sharp as nature will allow. Well, at this point, we're going to give you a break from these presentations and check in live at the Mirror Lab to see what's happening. I think, yeah, we're going to start with the live camera images of the furnace rotating. These images are taken once per second, so it looks like a very jerky rotation, but trust me, it's really smooth, exactly like you saw in the video. And we want to let you know that there's a website that has a lot of interesting data that's kept up to date within a few minutes. Throughout the casting, it'll show the temperature of the glass and show live video images. We have cameras mounted in the ceiling of the furnace that give us a view of the glass as it's melting. And we'll put the link to this website in the chat so you can check it out for yourself. We also put together time-lapse movies from the images that you just saw, and those are available at the same website. We're going to show you the movie that's been made up to almost the present time from the images for this casting. We'll go through each of the 6 cameras separately. 3 of them have wide field, 3 are narrow field. These movies are sped up by a factor of 5,000 from real time. So they're showing what's been happening over more than a day. You see the glass soften, and it's forming a pool of near liquid glass on top of the mold. It's really not liquid. It hasn't reached that consistency of cold honey yet. It's still too thick to flow down through the half-inch gaps, or at least it was at the time this movie was put together. On the side of the mold, as you see here, we mark the height in inches above the tops of the boxes. We're getting 5.5 inches of glass. That means that it's all on top of the mold. It hasn't started flowing down yet. In real life, it is actually flowing down right now, but it'll take 4 hours for it to completely fill the mold. Okay, and I think we're now ready to go back to the presentations. So I'll turn it over to Buell again.
Thanks, buddy. So next we're going to be learning what's going to happen to the mirrors after they're made, how they get put into the telescope. And for that, I'm going to turn it over to Jim Fanson, who will tell us about how the remarkable team he is leading is building the GMT in Chile. Jim?
Thank you, Buell. After the mirrors are fabricated, they're placed in custom shock-mounted steel transport containers for the more than 5,000-mile journey to the observatory site in Chile. They will proceed by wide load truck from Tucson, Arizona, to a major port city in the US, probably Houston. And from there, the mirrors are shipped by sea through the Panama Canal to a port city in Chile. The mirrors are then transported by truck along the Pan American Highway to the Mountain Access Road and then up to the observatory site at Las Campanas at an altitude of about 8,200 feet above sea level. This slide shows an artist rendering of the completed observatory at Las Campanas. Chile is a wonderful host for GMT, and our site offers some of the darkest skies and best observing conditions on Earth. The large building is called the enclosure, and that protects the telescope, which you can see through the open biparting shutters. The building to its left is the summit support building, which is dedicated to the processing of the primary mirrors. The mirrors are unloaded from their transport containers and placed in mirror cells that contain hundreds of mechanical components that are used to control the position, the shape, and the temperature of the mirrors while they are in the telescope. Up to this point, the mirrors do not have a reflective coating on their front surfaces. So a large coating chamber in the summit support building is used to apply a thin reflective layer of aluminum to the front surface of the mirrors. This coating is about 100 nanometers thick and uses 15 grams or about a half an ounce of aluminum per mirror. Once the mirrors are coated, they're moved to the enclosure building and lifted by overhead crane through a hatch in the observing floor and integrated to the telescope structure. You can see here the 7 mirror segments, one in turn being attached to the telescope structure. The telescope optics are aligned by means of laser trackers and other metrology tools. And the telescope as a system is commissioned over time. Subsystems are integrated and brought online. The construction at the observatory site in Chile has progressed through completion of dormitory and dining facilities, power, water, and other infrastructure, and hard rock excavation of foundations for the telescope and the enclosure. And the next step in construction will be the pouring of the concrete foundations. Back over to you, Bill.
Thanks, Jim. Now, Dennis Zaritsky is going to share with us how the operating GMT will push our science forward for at least the next 50 years. Dennis?
Thanks, Bill, and good afternoon, everyone. What you're seeing now is a rendering of that same telescope and observatory, but in operation at night, open to the sky, making observations. And the primary mirrors you've been hearing about are the most important part of the telescope for several reasons. First, they determine how much light we catch from the sky, which directly translates into how faint an object we can see, and it defines the sensitivity of the telescope. Second, they're responsible for forming images of the sky that are as good as nature allows, but to do that, the mirrors need to be perfect. As Buddy was explaining, with bumps and shape errors smaller than 1/1000th of a human hair. So pretty amazing. Third, and less obvious, is that the shape determines the field of view of the telescope, meaning how much of the sky we can see at any one time. That's crucial because a wide field of view lets us study more objects faster. That's the difference between seeing something that could be a fluke or discovering a whole class of object that we can study to learn something fundamental about the universe. The last thing I want to say about these mirrors is that the diameter of the whole set of them is what limits the sharpest image we can make due to the quantum mechanical interaction of light with the mirror itself. That's called the diffraction limit of the telescope. The bigger the mirror surface, the better the diffraction limit, the better the resolution of the telescope, the finer detail we can see. So it's clear that the mirrors are really the heart of this telescope. The 7 mirrors work together on GMT, so they form a single perfect surface to focus light, even though the 7 mirrors don't touch. Ultimately, they form images that are 10 times sharper than those made by the Hubble Space Telescope, with 80 times the collecting area. So increases in both sensitivity and resolution. Again, the glass itself is just the structure of the mirror. The reflective part will be that thin layer of aluminum that Buddy and talked about. So this whole telescope is being designed essentially to carry that thin layer of aluminum, supporting it in the perfect shape, pointing it anywhere in the sky, so that we can catch and magnify the images of objects all over the sky. So what are we going to be able to see? Well, with the sensitivity and resolution these mirrors provide, we'll be able to see fainter objects than ever before, including all kinds of objects, nearby objects that are intrinsically faint, like planets, or objects that are intrinsically bright and only appear to be faint because they're so distant, like galaxies that are literally on the other side of the visible universe from us. Moreover, we'll be able to collect enough light from these objects so that we'll not only be able to find them, we'll have enough light to spread it out into wavelengths, make spectra. This in turn allows us to measure such things like the chemical compositions of objects, temperatures and surface pressures of stars, motions of stars and gas within galaxies, and so on. With these spectra, we go beyond just seeing the objects to understanding how they form and evolve. What do we learn from those observations? Well, we know from past experience that huge leaps in sensitivity and resolution, like those that we're going to have with GMT, are going to revolutionize our understanding in all areas of astronomy. from the formation and evolution of planets and stars and black holes and galaxies to the universe as a whole. We'll even learn about things we can't directly see, like the nature of dark matter and dark energy. So let me just focus in on a couple of examples. So this slide is showing you the amazing system TRAPPIST-1. It's an artist's impression of the system, which is astoundingly the home to 7 rocky Earth-like planets. And this is just one of over 4,000 nearby stars that we already know have planets that range from gas giants like Jupiter to rocky metallic ice giants like Neptune to water worlds and everything in between. From the ones we've found so far, we extrapolate that there are billions of planetary systems in our galaxy. Of the 4,000 that we have already identified, hundreds are rocky Earth-like planets, and hundreds are also at the right distance from their parent star to be in what we call the habitable zone, which means that they have the right surface temperature to have liquid water. Some of the planets in the TRAPPIST-1 system happen to be both Earth-like rocky planets in the habitable zone, which starts to get really interesting. With the GMT, we'll be able to take images of the nearest of those planetary systems to actually see them orbiting, measure the temperatures and reflectivity of the planets to understand their composition, and even take spectra of the atmosphere to look for the right combination of molecules that will tell us if those planets actually host life. Now, let's go to the other extreme, the most distant objects in the universe. This image is called the Hubble Ultra Deep Field. It's not an artist's impression, it's real, and it was taken with the Hubble Space Telescope. Almost every object you see here is an entire galaxy. In this image, you can see objects about 100 million times fainter than what you can see with your naked eye. Some of the galaxies in this image are faint because they're intrinsically faint, they just have few stars. But some, like the objects that are going to be circled now, are faint because they're amazingly distant. Now let's zoom in on some of those faintest objects. We already know that the galaxies you're looking at here are over 13 billion light years away, which means that the light we're seeing now was emitted by these galaxies over 13 billion years ago and has been traveling to us ever since. So GMT doesn't just allow us to see objects at large distances, it effectively lets us look back in time. These are really baby pictures of the first galaxies. Now, the timing means that these galaxies formed less than 300 million years after the Big Bang, which in astronomical terms is amazingly fast and a bit of a puzzle. To understand how they formed and how they become the galaxies we see around us today, we will have to be able to study them in detail, not just the smudges as you see here, and GMT will let us do that. Remember, we'll have 10 times better resolution than what's shown here and much more sensitivity. We'll be able to measure the chemical compositions, the motions of gas and stars within these galaxies, and even measure their masses, all of which helps us understand how they formed, what's lighting them up, and begin to place them in the family tree of the objects we see today. So these are just 2 examples of things we know we'll learn. We'll learn more about these objects. The unexpected discoveries will be endless. That's what these mirrors will do for us. That's what the telescope will help us learn. And that's ultimately why we're building the Giant Magellan Telescope. All right, back to you, Buell.
Thank you, Dennis. And thank you, Jim and Buddy. And they're going to rejoin us. And I also want to welcome Roger Angel, who's going to join us for the Q&A session now. So if you will all start your video, I will start directing questions from the Q&A session. And from Ken Alevy, if the telescopes today, including Hubble, give an approximate age to the observable universe at 13.8 billion light years, will Magellan add to that number? Dennis, would you like to answer this question?
Sure, I'll start on that. So no, they won't change that number exactly. That's a pretty well-determined number now. What it allows us to do is push back our view all the way as far back as we can. And so to study how those first objects formed. So in a combination with GMT and other great telescopes that are coming, it's really going to open up this window of the formation of the very first objects. That's what we're excited about.
So we have a couple questions about why we use glass and how long it takes the glass to anneal. So I'm going to ask Roger, why did you pick glass instead of a metal alloy or some other substance to provide the structural support for our mirrors? And how long does it take for the glass to actually anneal?
Well, why do we use glass? Actually, Newton figured this out. It's an incredibly stable material. So once you polish the shape on the surface, in the future, in 100 years' time, it'll either have the same shape or it'll be broken. Those are the only two alternatives. So as long as we treat the mirrors carefully, all this work that we put into making the shape is going to last. The other thing, and we use a special glass that has very low expansion. The temperature does change night to day, and we try to follow that. But by using the lowest possible expansion, then the shape change from the thermal differences is minimized. So that's why just about everybody uses glass. Sorry, there was one more end to the question.
Yeah, how long does it take the glass to anneal when we're casting? I think Buddy.
Yeah, it's about 2 months. And in the critical part of that, when it's freezing and we're going to lock in the shape, then we cool it about 1 degree centigrade a day, right? So incredibly slowly, just for maybe 30 or 50 days.
Thanks, Roger. Hal Heaton asks, will there be an adaptive optics subsystem supporting the GMT? And if so, where do the beams emanate from on your schematic diagram? So that's a great question. One of the things that allows our telescopes to reach the diffraction limit and take images sharper than the existing space telescopes are the adaptive optics systems that we'll deploy on GMT. And GMT will have an adaptive secondary. I'm going to ask Buddy to describe these remarkable shells, because Buddy was involved, as was Roger, in developing the first adaptive secondaries on some of our other telescopes, like the MMT and the Large Binocular Telescope. Buddy?
Right. Oh, okay. Well, you may know that adaptive optics has been around for several decades now, and it gets better every year. It's not all the way there, but it gets better every year. But a big innovation was something that was started by Roger and one of his colleagues, and that's to make the deformable mirror of the adaptive optics system be the secondary mirror of the telescope. So it's an essential part of the telescope already. You're not adding any optics in order to do this adaptive optics correction. But it means that the secondary mirror, instead of being a thick, stiff piece of glass, becomes 1.6 to 2 millimeters thick. In the GMT case, the design is for 2 millimeters thick. The GMT secondary mirror is segmented like the primary. In fact, every primary mirror segment has a matching secondary segment. The whole secondary is a little over 3 meters in diameter. So each segment is a little over 1 meter in diameter, but only 2 millimeters thick. And its shape is controlled by approximately 700 voice coil actuators. So they're little electromagnetic actuators. We bond permanent magnets to the back of this thin shell of glass, and then there's an electromagnet in the supporting structure that changes the force and can do so tens of thousands of times per second, so that the whole correction takes place a few times per second, measuring the atmosphere and then correcting, or measuring the wavefront error caused by the atmosphere and then correcting for it. But I don't know the answer to one specific question, which is where the laser guide star beams emanate from. I assume that's what that is about.
Okay, I'll ask Jim if he knows. Jim Hansen, do you know what the current design has for how the lasers would be launched? So lasers are launched to create a guide star that creates a point of light that's not at infinity, but far enough away that we can measure what's happening to the wavefront of light as it goes through the telescope system. So, Jim?
Yes, the lasers are launched in pairs from 3 stations on the telescope structure, and they're about adjacent. They're actually in between, at the outer circumference, or in between 2 of the primary mirror segments. So at 3 locations, equidistant around the circumference of the telescope, there are platforms that launch these laser guide stars.
So a few more questions for you, Jim. People want to know, when are the mirrors going to get shipped to Chile, and when will the telescope start operating? And someone very astutely points out there are a lot of earthquakes in Chile. Are we doing anything special to make sure our telescope really is around for 50 years?
Those are all excellent questions. I'll briefly cover each of them. We'll ship the mirrors to the site when we have a place to store them at the site. As we finish them now, we're storing them in Tucson. The telescope will be commissioned towards the end of this decade with 4 primary mirror segments of the 7. That will, in and of itself, give us a telescope larger than any telescope in existence today. And then we'll finish the build out of the telescope, including the primary mirror segments, in the early part of the next decade. With regard to the seismic hazard, Chile is an extremely seismically active area. So we are taking measures in the design of the telescope to protect the primary mirrors and other components on the telescope. The principal means of protecting the telescope from earthquakes is to place the telescope pier, which is a thick concrete ring wall that supports the telescope. That ring wall will rest on 24 single friction pendulum seismic isolator bearings that are designed to break away when the ground motion acceleration exceeds a certain level. So below that level, they'll remain stiff and rigid for the telescope to operate. When the earthquake motion becomes too severe, they will break away and allow the ground to move underneath the telescope without transmitting that acceleration or that force. There are other measures we're taking in the telescope and in the mirror cells to protect the optics, but the isolation system is the main protective measure.
Thanks, Jim. Next question is from Elaine Jones. I'm sorry, that was the earthquake one. Next question is, how do you get the mirrors out of the mold? And I'm going to ask Buddy to answer this, because the hard part is getting the mold out of the mirror. So Buddy?
Yeah, that's right. But to be complete about it, we do disassemble as much of the mold as possible. There's that tub, which is made out of silicon carbide cement, and we can take that off in pieces. That's external. Now there's a similar floor of the tub, which is attached to the bottom of the mirror after the casting, and that doesn't come off immediately. But we take off everything we can from the outside. And then to get at the rest of it, we've got to get the mirror off the turntable. So this is a pretty interesting mirror transport process, because you've got not only the glass, but a whole lot of stuff attached to it. So it's much heavier than the finished glass. We lift it off by bonding a steel frame to the top of the mirror with 36 like 2-foot diameter discs that are bonded to the mirror with a thick layer of very compliant adhesive, so it doesn't put stress into the glass. And then move it to the other end of the lab, where it can be turned into a vertical plane to give the workers access to the back of the mirror. And that is where the rest of the mold comes off. The floor tiles are removed just with ordinary wrenches. And then to get the ceramic fiber boxes out, which are trapped inside the glass during the casting, we wash it out with high pressure water, like one of those wands you'd get at a self-serve car wash. So that removes all of the mold, and you just got the single piece of glass at that point.
Thanks, Buddy. Next question is, will people still make big telescopes with single mirrors, or is your technology of multiple segments making a single mirror going to be the new standard? Combined to make a single mirror going to be the new standard. So our telescope is not the only telescope that uses multiple mirrors. In fact, the University of Arizona and Smithsonian Astrophysical Observatory were involved in making a telescope in the late 70s called the MMT that used 6 mirrors together in one telescope. Now, they weren't phased into one mirror surface, but that was multiple mirrors. The Keck Observatory uses segments. The James Webb Space Telescope uses hexagonal segments. So there are a lot of telescopes that use multiple mirrors to make their primary. Basically, it's hard to make mirrors bigger than the ones we make right now if you still want to be able to transport them on existing roads, ships, planes. So at least for a while, we're going to be making them out of segments. Next question is, how will GMT compare to other large ground-based telescopes like the VLT in terms of light gathering ability? I'm going to ask Dennis to respond to that.
Thanks, Bill. So basically, the light gathering capability of a telescope is related to the area that the primary mirror covers. You can think of it like a bucket. You have a bigger bucket, you collect more rain. You have a bigger telescope, you collect more photons. And it's proportional to the area of the primary mirror. That's the sort of simple answer, but in fact, the sensitivity of the telescope also improves with the image quality. And so if you make sharper images, with GMT will make sharper images because of its higher diffraction limit, so you can focus the light into a smaller area and gain sensitivity that way as well. So there are a couple factors that help GMT make a big leap forward from our current generation of telescopes.
So Allison Hughes asks, what is the timeline for final completion and for the first public results? I'm hoping to still be alive, the question, there it is, still be alive to experience the preliminary results. So Jim, do you want to give us the current timeline for when, and this is, I don't want to put Jim too much on the spot. We still are a ways away to being done, but what's the current timeline for full operation of the observatory?
Of course, the schedule depends on many factors, but we would expect to finish the complete observatory and commission the full aperture in the early part of the next decade, and integrate the first generation of scientific instruments around the same time.
So there's another great question for everyone who's eager to see this telescope working is, what will the first targets for the GMT be to observe upon commissioning? So Dennis, as chair of the SAC, have the astronomers across the GMT community discussed this yet, or are people?
No, not really. The first instrument is slated to be the high resolution spectrograph. So, so the first data we get from it will not be a beautiful image, but it'll be a beautiful spectrum of something. But as far as the science targets go, for any telescope, it's always a process where a committee gets together, reviews the science, figures out what is most worthy, and gives time to that project. And so as we get closer to that time, I'm sure there'll be many proposals for the most exciting science to do. And some people will have to be called on to make that decision.
Thanks. Jim O'Leary asks, how will GMT compare to other large ground-based telescopes? Okay, I thought we answered this, but maybe not well enough. One of the things I'll stress about all the new facilities that are coming for the next 10 years is it's the combination of the telescope and the instrument, how you're measuring the light, and the science program that you're trying to undertake, the people that are coming up with the ideas of what you're going to look at, what questions you're asking. And the wonderful thing for us who are going to be using the GMT is there are other major facilities in Chile, like the Vera Rubin Observatory, which is making a huge survey of the sky over the next decade, deepest map of the universe ever made, or the ALMA sub-millimeter interferometric array, also in Chile, which studies gas in galaxies over all of cosmic time. We can make observations that are complementary to those facilities. Among the giant telescopes, like the 30-meter telescope and the ELT and GMT, the instrumentation is going to be different, and the capabilities are slightly different. Our telescope has a much wider field of view, how much of the sky we can observe simultaneously with one instrument, than the other two telescopes. The ELT is larger, so it'll have a better diffraction limit than the other two large telescopes. But working together, we're going to be pushing the science forward in the study of exoplanets, cosmology, galaxy evolution. Next question is from Paul Schultz. Sorry, that one we already asked. If there are no storage buildings at the GMT site in Chile, where are the completed mirror segments being stored? So as Jim mentioned, 2 of them are currently being stored in Tucson in a hangar. The 3rd mirror, we are going to finish polishing the surface to the final accuracy later this summer, and then it will go into storage as well. Segments 4, 5 are being worked on in the mirror lab right now. 6 is being cast, and segment 7 will be cast in 2 years. We have another question. Is there a big change in temperature at the observatory site? Jim, do you want to comment about the range of temperatures seen at Las Campanas?
One of the features of Las Campanas is that the temperatures are remarkably stable. The diurnal temperature variation is limited, and the swing throughout the year is also quite limited. So I don't have the exact numbers in my head, but it's much more benign temperature environment than at most observatories that we're accustomed to.
Thanks. Buddy, how long does it take to grind each mirror? Isn't each segment shaped so that they can act as one? So yeah, maybe you could explain what the difference is between like an on-axis and an off-axis mirror, and explain how long it takes to grind them and polish them.
Okay, so ordinary telescope mirrors, like before segmented telescopes, were axisymmetric, and GMT has one of those at the center of the telescope, but the other 6 are what we call off-axis mirrors, and they have a very different shape, and it's more challenging in the, not so much the grinding, but in the polishing and measuring. So they have taken us longer. We estimate on average the time is about 4 years for the complete manufacture of a mirror. We're always working on more than one mirror at a time, usually three or 4, and things, there, changes in priorities and interferences. So no 2 mirrors take the same amount of time. But it's roughly a year for the grinding of all of both the top and the bottom surfaces of the mirror. I should probably say the front and the rear surface of the mirror and the outer edges, and attaching some hardware, which will be a permanent part of the mirror that interfaces it to the telescope. So that's roughly a year, and then roughly 2 years for the fine grinding and then the polishing of the mirror, where the challenge there is getting down to that accuracy of 25 nanometers or a millionth of an inch. We start off from the casting with an accuracy of about 2.5 millimeters. So it's got to improve by a factor of 100,000 from there. And it just, it takes a certain amount of time to get each factor of 10, and especially the last one. So that is the bottleneck in our process. We work really hard to make it go faster, but that's where we are now.
Well, it's also a conservative process, right? We don't want to polish too much, because if you take away too much glass, you can't really put it back on. So Buddy leads our testing team, as well as Steve West and others are involved in testing the surface of the mirror in between polishing runs. So the polishing team will polish for 80 to 100 hours. Then we have to test the surface and then polish again. So it's a very iterative, careful process. And I'm sort of in awe of the patience and artistry that gets applied by the people at the Mirror Lab in order to pull this off. There's another question here that is right up Dennis Zaritsky's alley. We're asked, deep space imagery, what is it that allows us to deduce that there is dark matter and dark energy? And Dennis is actually part of the team that helped prove that dark matter exists with something called the bullet cluster. So Dennis, can you do, without any figures, an explanation of how the bullet cluster shows there's dark matter, and then maybe comment on dark energy?
Well, so the two quantities are measured quite differently. So the dark matter one is usually measured by trying to weigh objects and figure out how much gravity an object has. And that usually involves measuring how fast stars or gas are moving in that system. And then you can infer how much mass is there to hold it together. In the bullet cluster, we actually used light itself and saw how the gravity was affecting the light to make a map of the cluster, the bullet cluster, which is actually two clusters that are colliding. And that collision acted like an accelerator in physics. It sort of threw the system apart, and it separated the dark matter from the normal matter. And we mapped the location of each of those, and they were in different locations. So you could see that the dark matter actually existed and wasn't something associated with the normal matter. Dark energy is measured more by looking at the geometry of the universe. Basically, we act as surveyors. And so we look at distant systems and try to figure out the geometry by knowing either how bright something is that's far away or knowing what its size is. And that allows us to measure distances. And we can do that across the universe at different redshifts, at different distances and times. We can measure the geometry of the universe. And that geometry then tells us what, if there's any dark energy, and if there is, what it is.
Thanks, Dennis. I love this next question. Anonymous asks, for some of us seniors, can't you complete the Magellan sooner? And I'll tell you that you don't have to be a senior citizen to want it to be finished sooner. Building these giant telescopes is a little bit like modern cathedral building. The people that start them aren't the ones that get to finish them, unfortunately. As I mentioned earlier, Roger started the Mirror Lab almost 40 years ago. As Jim mentioned, we're going to complete this telescope at the end of the decade. So I hope you, Mr. or Miss Anonymous, I hope you have a long life and you get to the next decade. That's when the telescope will start producing results. Fortunately, someone asked here, how do you future-proof yourself against technology overtaking your current project when it takes so long? And I'll mention Roger is always coming up with a new design for a new telescope that does something new. But one advantage these giant telescopes have is, unless you build something that's bigger, the diffraction limit still wins, and the light gathering power still wins. But I'm curious, Roger, do you have any ideas for how you could make the GMT obsolete before we finish it? And if so, please don't share them with me.
No, I can't make it obsolete, probably for the next 20 or 30 years, right? And it will never be obsolete. In the thing that it does really well that we've talked about, it is so big across that sets how sharp the resolution will be. And so making sharp resolution images, there are ways to make telescopes that collect photons in the way that Dennis talked about in a bucket. And if you're not too fussy about the photons, you could make cheaper buckets, but you'll lose something if you do that. I did want to come back to Dennis's thought on what we do first with the GMT. And as he says, we do have a spectrograph. And the thing that excites me and has got me excited about mirror making and this science again, is that some of these planets of other stars are orbiting stars where they block the sunlight, the starlight. And at that time, you can see what the atmosphere of the star is made of. And one of the first things, if I'm lucky enough still to be alive when this goes at the end of the decade, when you see the spectrum of a planet imprinted on the star, you can look for life on that planet because life generates oxygen, or at least it does on our planet. So for the very prime examples of that, the GMT should be able to actually look not for planets that could take life, but which actually have life on them now that's generating oxygen. And that's one of the things that a spectrograph can do, right? It doesn't take a picture, but if it tells you there's life there, that's incredible.
I agree. That is one of the reasons we're building the telescope. There's a quick question is, do you create spare mirrors in case one breaks? We actually aren't making any spares to guard against breakage, but we are planning to make an 8th mirror that can swap in for one of the petals, one of the 6 outer ring mirrors, while that mirror is being re-illuminized. We do keep developing new techniques for protecting the surface, the aluminum coating, so that we don't have to re-illuminize it too often. But the surface will need to be recoated on each of the mirrors. So having an 8th mirror will help make sure that the whole telescope is operating as much as possible, even when we have to take one of those segments out. We avoid, as much as we possibly can, doing anything that puts the mirrors at risk for being broken. And then let's see. Is there a next generation of cameras on the drawing board planned for the telescope? And so yes, and I'm going to ask Dennis to mention what the first light instruments, well, the first generation of instruments are going to be for GMT. It's both cameras and spectrographs.
Yeah, so there's a suite of instruments already being planned. There's 2 optical and 2 infrared, so we cover a large wavelength range. There are high resolution spectrographs, so we can spread the light out a lot and look for fine details, measure the sorts of, make the measurements that Roger was talking about atmospheres of planets, and low resolution spectrographs so that we can look at fainter objects and make the necessary measurements there. So both in the optical and in the infrared. There are the high resolution spectrographs will look at a single object at a time. The lower resolution spectrographs, the optical one has the capability to look at multiple objects at a given time. The infrared one has the capability to look at a piece of space, a small chunk of space, and get spectra all across that area of space at very high angular resolution. So those are the set of 4 that are coming, and there's talk of the next generation, and there are concepts for wide field infrared spectrographs, an infrared spectrograph that could look at multiple objects. There's another capability where we could take advantage of the larger wide field of the telescope and get spectra of many objects, hundreds of objects at a time over that. There's been proposals for going farther in the infrared and getting more towards what's called the thermal infrared. So there are many concepts bouncing around. There's no commitment yet to go to those yet, but people are certainly excited and thinking about it.
And I guess that's one of the advantages that we have for a ground-based telescope, is that we can have multiple generations of instruments over the next 50 years, taking advantage of technology advances. And
right, that go back to the future proofing.
That's right.
Yeah.
We have a question on how do you get the hole in the center of the primary mirror? So this is in segment 4, Buddy. How did you get the hole in the center mirror?
Yeah, well, if I could back up for a second, why is there a hole in the center of a primary mirror? It's because these instruments Dennis talked about go behind the primary mirror. You would never want to have them up above the mirror. They're big and heavy and complex. So the light hits the primary mirror, then it comes to a focus, but either before or after it gets there, it reflects off a secondary mirror and then comes back down through this hole in the primary. And GMT, being a segmented telescope, a segmented mirror telescope, only needs a hole in the center mirror, whereas more traditional telescopes all have a hole in the center. Anyway, we cast it in. You saw the mold that we use for segment 6, which is an off-axis mirror, and it just has an outer tub that holds everything in it. But for the center mirror, there's an inner tub wall as well that keeps the glass from getting into the middle. So it's a ring, it's an annulus that leaves that center hole.
Thanks, buddy. David McIntyre asks, are all 7 mirrors centered parabolas or are 6 off axis? And that's a really good question. They all start off being cast as symmetric around their own centers, but we need them to be symmetric around the center of the 25-meter primary mirror. So Buddy and his team have to convert, they can polish the 4th segment as a on-axis symmetric mirror, but the petals, the ones in the outer ring, all end up being off-axis. What are the advantages of the 7 mirrors versus the mirror system used in a Keck-type telescope? I'm going to give this one to Roger. Roger?
Yeah, there are some sort of technical aspects with a mirror with dozens or hundreds in the case of big telescopes. Then you never quite perfectly get these segments together, and so you get some scattered light. And in some aspects of looking, for instance, at planets around stars, we do better with GMT because there's a very limited amount of scattered light from the segments. So it's I don't know what more I should say there, but I think the cleanliness of the optics and the way the primary, the 6 or the 7 secondary segments work with the 7 primary segments allow us to be very clean about how the light comes to a focus. And when you are trying to do very high contrast, that has an advantage. So I think in the exoplanet imaging, we will be able to do things, I think, that the other telescopes can't.
Thanks. We have a question, how is the reflective aluminum surface applied? And the question, then vacuum deposition, question mark, and that is the answer. And then another question is, I understand, this is from Sid Leach, I understand that GMT could be put into operation with only 4 mirrors. Is it likely that might happen, or is it more likely that by the time the telescope mount is completed, all 7 primary mirrors will be ready? Well, certainly at the Mirror Lab, we'll try and get them ready as soon as possible. But Jim, do you want to comment on what your current plan is for how many mirrors you want to commission the telescope with?
Right. So even if all of the mirrors are at the observatory site waiting to go on the telescope, we will still be commissioning the telescope incrementally as we add the optical elements. We need to get some experience with operating the mirrors and in pairs with the secondary mirrors. And by the time we have 4 mirrors on the telescope, we will have a telescope larger than any telescope today. And there's useful science we can do there. There'll be some fraction of time, I think, that'll be devoted to doing early science while we're still doing engineering on the observatory and completing the commissioning. So we want to get on the sky as early as we can to do useful science while we integrate all of the optics and bring the telescope online.
Thanks, Jim. Hal Heaton asks, what is the envisioned initial operating band for the GMT? Any extension to the near UV? How far into the near IR? So the question is, over what wavelengths of light will the telescope operate? So Dennis, how far into the near UV are the current instruments planned to operate, and how far into the infrared?
So that's still a little bit open, but it's going down to below 4,000 angstroms. So definitely into the blue. Whether we can get all the way to the edge of the UV cutoff in the atmosphere is still challenging. There have been some proposals for instruments to push that way. So there's a few hundred angstroms there. That's always a bit challenging for instruments on the blue side. On the red side, again, it's the atmosphere causes problems, but there are windows, and you could go farther and farther into the infrared where there are some windows you can observe. Currently, we're not pushing out to 10 microns, as far as you could imagine ground-based telescopes going. The instruments we have aren't doing that, but that could be done. Currently, though, we have two near-infrared instruments that would be going in beyond a micron, but not up to multiple microns.
Thanks. From YouTube, we had a question. Are there any larger telescopes or farther seeing telescopes under construction or planned? So there are 3 giant telescopes currently in various stages of construction: the Giant Magellan Telescope, the 30-meter telescope, and the extremely large telescope. You might notice that we're not incredibly creative in naming our telescopes, but all 3 of these are really giant compared to the current generation of telescopes. But how sensitive a telescope is not just a function of its collecting area, but how many reflections you have to go through to get the light from your astronomical target to your instrument. And so the exact answer of who sees the farthest depends a little bit on the instrument and telescope combination. But the European extremely large telescope has a primary mirror made out of hexagon segments that'll be 42 meters in diameter. The 30 meter is 30 meter, and we're 24.5 meters. Next question, or it's a comment from a 14-year-old who said, I found this very interesting and hope to go to the U of A in the future. Thank you for the presentation. You're very welcome for the presentation, and 14 is a great age for maybe getting to use the GMT for your career. So you're the generation that's going to really get to exploit these wonderful facilities. Jack Alexander asked, will the GMT provide more info than space position telescopes? So it's going to provide complementary data. Reasons for going to space include observing at wavelengths that you can't reach from the ground, and to be able to get high spatial resolution. The same telescope in space will outperform a telescope on the ground of the same size. But it's incredibly expensive to make a giant telescope in space. The dominant cost is just getting the mass of the material up into space. So James Webb, NASA's next big space telescope, is going to be 6.5 meters. It's going to be a fantastic observatory. We have faculty at the University of Arizona that have been involved in building the primary instruments for it, but it's still only going to be 6.5 meters in size, and it did cost over $10 billion to build. GMT is going to be 3 times bigger, be able to have spatial resolution that's 3 times as good. And at the optical wavelengths that we'll be operating, it will outperform the James Webb Space Telescope. So we need, unfortunately, astronomers, we're fairly ambitious in our ask to all of you taxpayers. There's always more that we need in order to answer the really challenging questions. And we're really grateful to all of you that sometimes our requests actually get answered, and we really appreciate it. Ed Reed asks, is the diffraction limit set by each segment or the diameter of the assembly of the segments? So Jim, do you want to answer that? Or should I hand that off to Dennis? And it looks like, am I still connected? Dennis?
Yeah, I can take it. Yeah.
All right.
Yeah, so it's the full set of the mirrors. So it's across the whole set of the segments.
I think we're finally getting to Zoom limit.
Okay, was my answer clear or not? Did it get garbled?
I'm not sure, but I'll just clarify in case it was garbled that in order for the diffraction limit to be that of a 24.5 meter telescope, the mirrors have to be positioned accurately enough with respect to each other that they work as one surface. Alan, can you tell me whether we're still understandable or not?
There's some kind of like reverb that reminds me of Dodger Stadium, but
Okay.
it's occasional.
Okay, we'll press on a little bit longer. Jack Everett asks, do the low temperatures that will be encountered at the location require any special procedures to protect the mirrors? The quick answer is no. They operate fine under the range of temperatures that they'll experience. There's a question here that I honestly don't completely understand, but we should try to answer it. Do the adaptive optics in action sing in quotes? So I'm not sure what that question asks. The mirrors are being changed in their size, their shape, close to 1,000 times a second. And they work, the 7 secondary adaptive secondaries, as Buddy was saying, that are all very thin, work together to create a corrected wavefront for the light that originally got distorted as it went through the Earth's atmosphere. Where are the secondary mirrors made? So Jim, if our connection's working, do you want to say where the secondary mirrors are going to be made?
Sure, I'd be happy to address that. There's an Italian consortium called Ad Optica, which has made a specialty of building these types of deformable mirrors. And we are planning a 4th generation mirror from that team, and actually using the funding we've received from the National Science Foundation that Buell mentioned. We're starting the fabrication now of the first off-axis adaptive secondary mirror. They've not been made in an off-axis shape before, and so that's a technology demonstration that we are undertaking at the moment.
So there's a question, why is the telescope named after Magellan? So I honestly don't know with absolute certainty the answer to that question. I'm looking at Dennis and Jim. Maybe I should have Jim do it. I do know that there are 2 6.5 meter telescopes at the same site called the Botta and Clay telescopes. Each one has one of our Mirror Lab mirrors in it, 6.5 meters in diameter. And they were called the Magellan telescopes. I believe that was because of the Magellanic Clouds being accessible in the south, but I don't know that with certainty. And a lot of the institutions involved in the Giant Magellan Telescope project were involved in the Magellan Telescope project. But Jim, do you know the history of the name GMT?
What I've been told is that the original Magellans were named after the Magellanic Clouds, which are very prominent in the southern sky. We're at the same observatory location as the Magellan telescopes, but we're bigger, so we're the Giant Magellan.
Got it. Mary Jo Kedu, apologies if I'm mispronouncing your name, says, what will the approximate cost of this project be? So Jim, as project manager, do you want to answer that, or do you want me as a board member to answer it?
Well, what I would say is that GMT is about a $2 billion enterprise, and it's it's a modern marvel, and we shouldn't be too surprised that it takes considerable resources to build a machine of this scale.
Thank you. Anonymous asks, how powerful and what wavelength are the guide star lasers? Are they CW or pulsed? I don't know what the current design is, Jim. Do you?
Yeah, I believe these are pulsed lasers. There's an increasingly common use of these in observatories, and these are now basically off-the-shelf products that you can procure. We don't plan to procure them for a while because we won't need them for a while. We don't need to invent them. And the technology continues to improve over time. So when the moment is right, we'll make a final selection of lasers.
Dan asks, what impact do you expect on GMT from mega satellite constellations currently being deployed? So for observatories that have a significant field of view, and we do, this is a concern. Our field of view is not as big as the Vera Rubin observatory with the large synoptic, which is doing the large survey of space and time, making a huge map, and they're very worried about the impact of these constellations. Dennis, has the SAC discussed this at all?
Only briefly, so we have not made a detailed study, but we also have a little more flexibility in where we point at any given time. We're not trying to map the whole sky all the time, so we might be able to avoid the worst of it.
Joel Alpert asks, 2 billion spread over the US population is $6 per person. What a deal. Thank you for that support. And it is actually an international project. So it's not, as I mentioned, institutions in Korea, Australia, and Brazil have also provided a lot of the funding for the observatory. Michael asks, do you think quantum computers will be on board? How do you think this will affect what you have built and the possibility of seeing farther out? That's a great question. I don't know enough about what quantum computing is going to do. Have any of my colleagues thought about that? Dennis?
Well, I'd only say that computational power comes really into play in the analysis and interpretation of our data usually. So I think anything that increases our ability to do more computation will be very beneficial in theoretical simulations, in analyzing large data sets, more than in running the telescope itself.
JP Foster asked, does dew ever form on the mirrors? I can imagine dew points are pretty low. And then there's, I'm sorry, I visited the site near La Serena, and this one would blow that away. So we don't intentionally let dew condense on the mirrors, but most observatories have unfortunately had that occur. We usually try and shut down operations and close the enclosure and protect the mirrors before dew would actually condense. Hal Heaton asks, I'd be curious as to Roger Angel's perspectives on what it took to initially establish the Mirror Lab and to develop the recognition and infrastructure necessary to establish its current capabilities. Roger.
Oh boy. Well, the very initial step was with then my student John Hill, who now is at the LBT. And we had to first of all get the idea. So the first mirror we made was 2 feet in diameter, and we melted it in Stewart Observatory. Then we got a bit more funding and made 6-foot diameter mirrors in what was a Jewish temple just at 6th Street in Campbell. And then we got, on the strength of what we've been able to demonstrate there, Jeff Burbage at the National Observatory then actually persuaded the NSF to let some of his budget go out and start the building of the Mirror Lab, where we already had in mind that the limit of 8 meters, which is as big as you can drive on the freeway, was where we wanted to get to. So it's a balance of funding, but we did get funding initially to get started with the Mirror Lab.
And then it's taken an awful lot of work by the whole team at the Mirror Lab to complete projects, to build up confidence in other people that wanted to then ask to do a new project. The Mirror Lab's been funded by the projects that it's been part of. It's not been supported by state funding. It's been supported by sponsored projects. Okay, we're going to wrap up on questions pretty soon, but there's one here that I know Jim doesn't want to ever have to actually try to answer. It says, after the bearings break in an earthquake, how will the telescope operate?
So I'm not sure which bearings are being referred to, but if it's the seismic isolation bearings, those bearings should not break in an earthquake. The way these bearings are designed, they're bowl-shaped steel surfaces that are attached to the foundation part of the pier, and then the part of the pier that the telescope is attached to rests on sliders that can slide on this concave bowl shape. So as the ground moves, the slider essentially climbs up this towards the edge of the bowl, and that lifts the telescope vertically, and that creates a restoring force. So what you essentially have created is a very low frequency oscillating mode of the telescope on the bearings. So the bearings are sized so that we will not exceed the allowable motion of the bearing. The telescope can move 7/10 of a meter on either side. So the bearings are quite large. So we don't expect there to be damage from the bearings, but if there is, we will have spare bearings down in the foundation so that we can replace the bearing if that needs to be done.
Thanks, Jim. And I see someone has their hand up in the participant list that we don't have the ability to call on you, Terry. So if you want to type in your question, I'll wait a second in the Q&A spot. But as we start to wrap up today, I want to thank all of our panelists and those that helped put this wonderful event together. And I also want to call out everyone at the Mirror Lab, especially the lab manager, Stuart Weinberger, who over the past year managed to keep the lab operating safely during a pandemic. I just think it's an incredibly remarkable achievement that they've been able to keep everything running safely, both for the hardware, but also for each other, and managed to keep the production of these mirrors on track. And we, of course, haven't been able to do public tours. We normally have public tours every weekday. We've been closed to the public, but as the pandemic hopefully recedes, we will resume public tours again. And I hope all of you that are online have the chance to come and visit the Mirror Lab in person. One last question was, why Houston and not the West Coast? And so that's for Jim.
Yeah, good question. When I gave my remarks earlier, I said probably Houston. We could go to the West Coast. It's actually closer to get to San Diego or even Los Angeles than it is to Houston. But you have to take into account the path you need to travel and how easy it is to get under bridges and across roads and other obstacles. The last large mirror that was moved to Chile from the Caris lab was for the Rubin telescope. That's another 8-meter mirror, and that was moved to Houston. So we'll make a final routing decision when we do the final logistics study. You know, if I had to place a wager at this point, I would guess we'd probably do the same and move to Houston.
Thanks, Jim. So my thanks to everyone who participated from the public today. Constructing the GMT has already taken the efforts of hundreds of people for several decades. And we've discussed how almost 40 years ago, Roger and his colleagues began developing the innovative techniques that enable us to make the mirrors. Now, talented people from all over the world have come together in the GMT organization to construct the observatory that is going to enable our founding institutions of the GMT to explore the universe for the next 50 years. And what we learn, we're going to share with the entire world. And we're grateful for the support that you have given to us in the past. And we're really looking forward to your continued support. With your support, we will complete the GMT this decade. So thanks again for participating. We look forward to seeing you again as we complete major stages in the fabrication and construction of GMT. Alan, back to you.
Thank you, Buell. Well, we hope that everyone enjoyed today's live stream. and on behalf of the entire staff of Stewart Observatory, the Richard F. Caris Mirror Lab, the Mount Lemmon Sky Center, we thank you for your interest, your enthusiasm, and your support for our efforts. The work that we do, from the groundbreaking research to the fabrication of these giant mirrors to our public outreach and education, none of that would be possible without the philanthropic support of individuals and foundations such as yourselves. It is truly you who has continued to enable our work, and we thank you. We thank you for the opportunity to share it with you. For those of you who participated on Zoom today, a recording of the live stream will be available on our Mount Lemmon Sky Center YouTube channel at youtube.com/Mount Lemmon Sky Center. And for further information on the Richard F. Caris Mirror Lab, Mount Lemmon Sky Center, or the Giant Magellan Telescope, visit our websites. The links for both the YouTube channel and the websites were included at the bottom of the confirmation email you received this morning. We hope that you will maintain your engagement with all of our space science programs and perhaps visit us soon in the future. Again, thank you for joining us today.